it actually wasn't true. It actually had recorded it. So I put it up. Where is the meet? What the heck? Okay, good. It's been a hell of a day, hasn't it? It's been a hell of a day. I'm exhausted. And we have a big thing to do today. We're starting to do entropy calculations today. It's all happening. You know, I do have a quiz that I'm going to give that I, will email. I pretty much have it done. I just have to get it out. And yeah, I'll try to make sure it's, I don't think it's as long as the others, but it doesn't have any entropy on it. So anyway, so that's what I have. I have to send that out. And I got to record. I still don't think I've hit that button. Oh, no, I did hit it. Okay, there we go. Yolanda, I'm looking at your pictures. All right. Well, I'm going to share my screen.
Sorry, that's mine. Let me mute that.
Oh, that's not Yolanda's screen. It's Jack's screen. I thought it was a little weird.
I think Jack's implying that our homework is a lot harder than the examples in class.
Well, at least it's special problems.
Well, I don't know about that. I do a lot of problems in class. I think it's just easier for me to do them than for you to do them.
I don't even know what that thing is.
I don't know. I just saw that today and it made me think about this class.
Oh, wow, that's great. I don't know what the heck is going on. I seem to have got like Zoom went somewhere. Oh, there it is. Okay. All right. So I was going to share the screen. And there's OneNote. Nobody has anybody actually come to, like asked me to meet them for an office hour or anything. So, I mean, until you do that, I don't think your complaints are valid. You can always try to get me to help you with something, but nobody ever seems to want to do that. I don't know. It must be very scary. All right. So I'm going to be giving a quiz soon. I'll probably email it tomorrow. And I'll give you about a week to do it. As you know, I'm very loose about that. So if you need a little more time, it's not usually a problem. And so we're going to continue talking about entropy. And okay, so last time I kind of gave this sort of, I don't know, a little bit different, talk about something in this course, because it turns out that what I was trying to show you yesterday or Monday was that processes tend to do, like in chemistry, what tends to happen is the likeliest thing. And that's also the process that spreads the most energy. So I guess I would say that the likeliest, and I've written this down before, the likeliest thing to happen happens. And also energy gets spread around. spontaneously. And we also saw that matter gets spread around spontaneously also. But I explained, or tried to explain, that at least for the case of some gas molecules, that if you have double the gas molecules, you're going to have double the number, the ability to spread around thermal energy, so that like spreading so when matter gets spread around, you're actually spreading around energy as well, right? Because these gas molecules have thermal energy. If you put them all in one place, then all the energy will be compressed. If you spread them out, then that energy is spread out. So spreading out matter also spreads around energy. And then I also said that what happens in chemical reactions and in different processes is that systems tend to go to equilibrium. So if systems tend to go to the likeliest place and the place that spreads around the most energy, then it must mean that these things are characteristic of equilibrium, which is certainly an idea that I'm sure you've never heard about in another class. And that's really like the probabilistic approach to entropy. We know the second law, which I'm going to give you very shortly, says that total entropy increases, and that coincides. You know, if you're going to keep increasing the entropy spontaneously, that means that equilibrium has the most entropy, and it's also the likeliest place to go. So there's these probabilistic ideas that work into thermodynamics. And so what I call this the probabilistic approach.
Dr. Cooley, can I ask a question?
No, you can't. Yes, of course you can.
Yesterday you said that equilibrium has the max disorder likeliest state. It has a maximum energy dispersion and maximum entropy. But I mean, at least like the way I think of equilibrium is when I thought of equilibrium as like sort of like when it's all like, I guess, at a constant and not like spread out like entropy. I was just confused.
Equilibrium, once the system gets to equilibrium, it really stops going anywhere. It stops the entropy, the increase in entropy stops. In fact, we will, just like you think about chemical reactions going to they tend to minimize the free energy, which is the same as maximizing the total entropy, which we'll talk about this later. But like so what I'm talking about is the journey to equilibrium, the journey to equilibrium. But once you get to equilibrium, then going in any direction will not increase the entropy. It's almost like the maximum that you could get, and it's the minimum in free energy. So those two are like opposites. Total entropy and free energy are opposite to each other. So whereas you would have like the equilibrium is the maximum in total entropy. So S total would be at a maximum, and that would be equilibrium, right? So the journey to equilibrium, which can be approached from different directions, especially in a chemical reaction. It could go from products to reactants, reactants to products. But equilibrium is that stable place where the total entropy is at a maximum within the constraints of that problem. And we'll see soon that it's also where the free energy is at a minimum.
All right, so it's like pretty much like to reach, going into equilibrium, that's where you have the maximum of like everything, like entropy, energy, and all that, right?
Well, I wouldn't say energy and all that. I would say maximum entropy.
And maximum energy dispersal.
Okay. And maximum energy dispersal. Yeah, that's right.
Thank you.
And anyway, I'm sorry to say that we're not really going to continue with this probabilistic approach because it's really beyond our scope. And I, told you that if you ever have a chance to take a course in statistical thermodynamics, that's where you're going to do things like derive the enthalpy from first principles, like from probability. I mean, it's really amazing that it's like two parallel ways of coming at thermodynamics. The traditional way, we're talking about heat and work and all that stuff. And then there's the probabilistic way. So I'm really going to drop the probabilistic way because we really can't do much more with that with our level. So I really gave you a taste of that only, unfortunately. And so what I'm going to do is I'm just going to use more conventional methods. And this is what I'm going to do next. So this is my agenda, really. And the first thing is to give you the second law. And it has the word entropy in it. But I really haven't defined what that is yet, okay? But that sort of tells us where we're going, all right? And then the second thing I'm going to do is discuss and define entropy, or actually not entropy so much as the change in entropy. As I said, mostly in this course, what we're concerned about is the changes in thermodynamic properties. So that's what I'm going to start with. So here's the second law. I like questions. You can always stop me to ask a question, Jack, or anyone else. Okay. I wish there were more people here, but oh well. So the second law says, in the course of a spontaneous process, so this is a process that happens basically on its own, the entropy of the universe increases. And this entropy of the universe, so we're talking about it increases, that means the change in the entropy of the universe. So that's what we call total, right? That means the total entropy. We're saying the universe, but we really mean the system and the surroundings. Okay, so delta S total is greater than 0 for a spontaneous process. So this is like a quick, that's the shorthand way of writing the second law. However, there's another part of the second law, which is not as talked about. Like I think most people have heard the second law, entropy increases. But there's another part, and that says that, so this part is about a spontaneous process, but the second part is about a reversible process. And for a reversible process, delta S total is equal to 0. And so actually this sort of speaks to your question, Jack, because you asked about equilibrium. And at equilibrium, that's really when the process becomes reversible, and the total change in entropy would be 0 going anywhere there. You're kind of at the maximum. So we have really two different situations that are treated quite separately in this unit. One is for spontaneous processes, and for that, the delta S total is greater than 0, but for a reversible process, the delta S total is equal to 0. Okay, and so what does that mean, delta S total? That's the delta S of the system plus the delta S of the surroundings is greater than 0. Just use one R there. And so here, delta S system plus delta S surroundings would be equal to 0. And now, whenever we have a system property, what do? We don't put a subscript. So no subscript implies system. So we would write this simply as delta S plus delta S Sir is greater than 0 for a spontaneous process, and delta S plus delta S Sir is equal to 0 for a reversible process. Already I'm having a problem with the pen. Boy, this is fun. Yeah, nothing I ever try works with this. Oh, well. Okay, let's see if we can go a little longer. So, okay. So what if you had an isolated system? So in other words, the system was isolated from the surroundings. It couldn't pass heat back and forward. There could be no work going back and forth. So for an isolated system, the delta S surroundings would equal 0, because for the process, the system, it's undergone in the system and there's no contact with the surroundings. So the influence of the surroundings is nothing. Can you see this? You can't see this, can you? But nobody was going to tell me. They were just going to look at me with
I was going to tell you I would interrupt.
Yeah. Okay, there we go. Sorry. All right, so for an isolated system, there, you know, it's like the surroundings isn't involved. It's not in contact with the system. Surroundings in the system are not in contact in any way. So something can happen in this system, but it's not going to affect the surroundings. And so there will be no change in entropy to the surroundings. But if you had, so if you had an isolated system, delta S total is just delta S. So that means that for a spontaneous process, the change in entropy of the system would have to be greater than 0. And for a reversible process, delta S would have to equal 0 because there is no surroundings. It's all system. No surroundings. Okay. So that's the second law right there. To understand it, though, you need to know about entropy. And I insist that entropy is really not so mysterious. So we already know that entropy has a lot to do with dispersal of energy as heat. Okay, so heat has to be involved. So we know that entropy has to do with energy dispersal. And that is basically heat dispersal. So we know heat is involved. Heat has to be involved. So I'm going to tell you now the change in entropy so the entropy of the system or the surroundings will increase if heat is added to it, right? And of course, if it's taken away, then it would decrease. So delta S is proportional to Q, right? That's the first thing we know about entropy. If you add heat to a system, Q is positive. Delta S would be positive. Okay, so here's another thing. And that is, if you put the same amount of heat into a hot system as a cold system, it turns out that one of them is affected more. Okay, if you put the same amount of heat into a hot system versus a cold system, okay, it's going to matter more when you put it into the cold system. It's going to disperse. Heat will be, you know, in a hot system, you've already got a lot of energy dispersal. You've got the molecules moving around and spreading around that thermal energy. But in a cold system, that's not as much the case. So it makes a bigger difference to add heat to a cold system than to add heat to a hot system. So what we say is that the delta S is proportional to Q divided by the temperature. So it makes more difference to add heat to a cold versus a hot system. There's greater energy dispersal if it's added, if even the same amount of heat is added to a cold system. I have an analogy for this. I call it the tax cut analogy. And so what if you're giving a tax cut to the citizens of a country, and you give a tax cut to people who already have a lot of money? So tax cut to the rich versus tax cut to the poor, which makes a bigger difference. You know, it's the same amount of money, but it makes more of a difference to somebody who's poor. Okay, rich people already have a lot of money. They don't need any more. Poor people need more. So that's my tax cut analogy. This is like giving a tax cut to the rich is like a smaller entropy change, smaller money dispersal. But to the poor, it's a greater entropy change, greater dispersal of money. Anyway, this happens to be the way we start off talking about the change in entropy. So we've got heat and we've got temperature, and I call this a working definition. It's not the final definition, but it is where we start. Okay, so we're going to revise this definition because we have to. But for now, it's Q over T. So the thing is, and the reason we have to revise this function is because as written, this implies, well, as written, is this can entropy be a state function if this is the definition? If this is delta S, so what do you think about that? If we say the change in entropy is, I'm just going to put equals here. That's a working definition. Sorry, I meant to put that equal sign there. If this is delta S, can S be a state function? So, you know, you go from one state to another, you have a certain entropy change, a certain amount of heat has been transferred. what do we know about heat? Is Q a state function? Right? Like, for example, we've studied the isothermal expansion, takes an ideal gas from one state to another. You could do that reversibly, or you could do it at constant pressure.
Is it
right?
a state function that doesn't depend on the path?
A state function is path independent, right?
Oh, I had it backwards.
Yeah, yeah. So Q is not a state function. It is path dependent. So if this were the definition, the final definition of delta S, it would mean that entropy was not a state function, because Q is path dependent. Now, does that make sense? All right, so the thing is, and I'm going to argue this to you without proving it, although it can be proven, I'm just not doing that. So what use is a thermodynamic function that isn't a state function? Like, this would mean that the entropy of a system could differ when its pressure and volume and temperature and all the conditions are the same. And that's just not true. That's not ever good. That's not correct. So how do we understand entropy? Like, your intuition about entropy is that it's about disorder or order in a system. So if you take a sample of water, and you freeze it at a certain temperature, say minus 10 degrees at 1 atmosphere, and so you have frozen water, say minus 10 degrees C, 1 atmosphere, and you have a certain number of moles. And so that has a certain order or disorder. And if you then do something to it, you say heat that up and you boil that water, and then you, cool it back down, and you get back to the same state that you had before, it seems to me that the order or disorder is going to be characteristic of what the conditions are, the temperature, the pressure, that sort of thing, not going to depend on how it got there. So these are arguments I'm trying to make to convince you that entropy should be a state function. Okay, now I'm going to show you something else. So entropy, of course, like enthalpy and free energy and all those things, you can look entropies for things up in a table. So I could look up the standard entropy of 1 mole of H2 gas, and I get this number, or the standard entropy of HF gas or H2O liquid. So if entropy were not a state function, then I couldn't have a table of entropies. Entropy would have to be a state function in order for that to be true. So I guess I'm going to leave a space, because I'm going to put that in when I post this. So tabulated entropy values, standard entropies, would be meaningless if entropy were not a state function. And finally, I want to say that the fact that entropy is a state function is actually proven, for at least for a particular example, that Atkins uses something we call the Carnot cycle, which I will study in a little bit later, but it won't be to prove that entropy is a state function. We're not using it for that. So Atkins uses something called a Carnot cycle to prove that delta S for a cycle is equal to 0. And you remember that if you could show that the change in a parameter in a cyclic process is equal to 0, that's equivalent to saying that S is a state function. So, this is not something I'm going to spend all day on, but we're just going to have to accept that S is a state function. And so we need to revise the definition of delta S. To make it independent of path taken. So we have delta S equals Q over T. And now I'm going to change this. I'm going to change it. So how am I going to make it independent of path taken? I'm going to specify the path that's always used to calculate the delta S. And that is the reversible path. So I'm changing my definition of entropy to be Q reversible over T. Okay, which seems completely crazy, but that's indeed what it is. Well, it's not quite that this is not really the general. Let me show you what I mean. The general way, the more general definition is that the infinitesimal in entropy is dq reversible over T. So I can integrate this. Okay, and if the temperature is constant, then I can take it out of the integral. So I'll have the integral of ds, that would be delta S. So like from state 1 to state 2 would be S2 minus S1, or delta S equals, so this would be 1 over T times dq reversible. So that would mean delta S is Q reversible over T. So this is true at constant temperature. But what if the temperature is not constant? So this is what I said was the definition, but this is really only true if temperature is constant. So the more general one is that delta S is the integral of dq reversible over T. And this is if temperature is not constant. This is more general. Then you would have to actually integrate this dq rev, which seems like, well, what the heck is that? But, very shortly, I'm going to show you an example, so you won't necessarily feel that way for too long. Okay. So we have this crazy definition of delta S that we're going to start to work with. Okay, but I'm not ready to do an example yet because I want to point out some pretty interesting things about this. Okay, so let's suppose a system starts at state 1. Okay, and it goes to state 2 and goes to state 2 along a reversible path. Okay, then the integral of dq reversible over T, so the reversible path from 1 to 2, right? This is delta S. This is basically what I wrote here. Okay, but I'm doing this to point something out. And what I'm going to point out is that, so now what if the system instead, so what if instead the system goes from 1 to 2, so the same states, right? But along an irreversible path. So what is delta S for this process? Okay, and the answer is it's the same thing, because delta S is defined as going along the reversible path. So the delta S in this case, it's the same. So therefore, delta S for going from 1 to 2 along a reversible path is the same as delta S from 1 to 2 along the spontaneous path or irreversible. And they are both equal to the integral of dq rev over t from 1 to 2. They're both the same. So regardless of path, the change in entropy always has that value, and it's always calculated by the reversible path. So that's something you have to kind of, we're used to calculating work and heat and things like that by, the different paths. We have to make sure we, use the right path to get the correct answer. But in entropy calculations, these two would be equal. Okay, but didn't I say, didn't the second law say? Didn't it say that the change in entropy is greater than 0 for spontaneous and equal to 0 for reversible? Think about that for a minute. So didn't I just say that?
Would that mean that the DQ then is 0?
It's not what I'm getting at here, but we'll get there. So did I say that the change in entropy is greater than 0 for spontaneous and less for reversible? Then how can they be equal? Is that something that I shouldn't be pointing out, that you never would have dreamed that that was a problem? Well, anyway, my point is I didn't say this. I didn't say that delta S is greater than 0 for spontaneous and less than 0 for reversible.
You said it was equal to.
I know, I was talking about delta S total. That's the difference. So no, I didn't exactly say that. What I said was that delta S total is greater than 0 for spontaneous and equal to 0 for reversible. I wasn't talking about the change in system entropy, which is what I call delta S, right? I was talking about total entropy. So, you need to be very clear and precise in your language in this unit and be very specific about what you're talking about. So let me just go over this again. The second law says that for a spontaneous process, delta S total is greater than 0. I guess I just wrote it. For a reversible, delta S total is equal to 0. So it's the total change in entropy that the second law refers to. Okay. Delta S is the same for a reversible path and a spontaneous path. because S is a state function. It doesn't matter what path is taken. So what's going on here then? What's going to make this greater than 0 if delta S is the same? Well, it's got to be the surroundings. All right, so delta S is the same, but delta S surroundings is not the same. So when you have a spontaneous and a reversible path between the same two states, the delta S is the same regardless of how you get from point 1 to point 2, but the change in entropy of the surroundings is not the same. So that's what's different. So what I'm going to do is show you an example. And this is an example that we know well, right? It's the isothermal expansion. And it connects two states, right? And we're going to study this for the reversible and the constant pressure. So obviously the reversible path is reversible. The constant pressure is spontaneous. And we're going to just contrast what we get. And along the way, we'll talk about what the change in entropy to the surroundings is, because it has its own definition. Okay, so I'm going to start with isothermal expansion. So delta S is the integral of dq reversible over T. But of course, temperature is constant because this is isothermal. So I can take that T out of the integral sign. And so this is what I'm trying to calculate right here. That's going to be my delta S. Now, what is this dq reversible? Okay, well, we know for an isothermal expansion, we know that du, right, du is equal to 0. Is everyone with me on that? Remember, that's a change that's happening to an ideal gas. It's not a reaction. It's not a phase change. There's no temperature change. So the change in internal energy is 0. But the first law tells me that this is equal to dq plus dw. Okay, so if I'm talking about a reversible expansion, then I have dq rev and dw rev that are equal to 0, right? And what is dw reversible? Well, I've never written it that way, but I've written dw for the reversible expansion. Well, dw is minus p external dv, right? But if it's reversible, that means that p external is equal to the pressure of the gas, right? This is just the same as when we derived this for an isothermal expansion. What is the work, right? So this would be minus P dV, where this is the pressure of the gas. So that means that, so by the way, if these two things sum to 0, it means that dq reversible is the negative of dw reversible. So this here is dw reversible. So dq reversible is p dv. That's all it is. So if you go back, we had that this is the delta S that we're trying to figure out. And it's 1 over T times the integral of P dV. So delta S is 1 over T, the integral of dq reversible, which is 1 over T, the integral of P dV. That's dq rev. Well, that's pretty easy to do, right? Integral of P dV. P is nRT over V, using the ideal gas law. So our delta S is the temperatures cancel. So an NR can come out of the integral, NR, the integral of dV over V, which is NR log of V2 over V1. Okay. So delta S is NR log V2 over V1. And I could use Boyle's law because the temperature is constant. And this is NR log P1 over P2, which is also something you've seen before, right? Okay. All right. So that's what the delta S is for the reversible isothermal expansion, where the initial pressure is P1 and the final pressure is P2. But guess what? This is also the delta S for any irreversible isothermal expansion, right? Because delta S doesn't matter what path is taken, it's the same. So so this is delta S, for example, for a constant pressure expansion. So if the external pressure is P2 all the time, right? Because the final pressure is the same as the external pressure. So this is delta S for both of those processes. Okay, but what about delta S surroundings? Okay, I haven't said much about this, but here is the definition that we use for delta S surroundings. The integral of dq surroundings over T. Looks a lot like the definition of delta S, except for one big difference. And that is that this is not for the reversible path. It's for whatever path was taken. Okay, so this is not dq sur reversible. It's just dq sur. It's for whatever path is taken. Okay, so this is the infinitesimal amount of heat that is transferred for the particular process. If it's reversible, we would use a reversible path. If it's a constant pressure expansion, we would use that path. Okay, so I'm going to calculate this. I'm going to calculate delta S sur, 1, for the reversible path, and 2, for the constant pressure path. And these are both isothermal expansions. How are you guys doing? You following this okay? This is pretty, I don't know. It's a lot. It's a lot, really. All right. So okay, delta S surroundings. So I'm doing this for the reversible case first. So dq sur over T. Okay. So what is dq sur? I haven't talked about this much, but if you have a system and you have the surroundings and you have a heat that's transferred, say that way, whatever heat leaves the system, it has to go into the surroundings. Or whatever heat leaves the surroundings, it has to go into the system. So these things, dq surroundings and dq, right? That's for the system because it has no subscript. These are always equal and opposite each other. Okay? So they're always negatives of each other. So this dq sir is just minus dq. Remember, no subscript means a system. Okay. So now we're talking about for the reversible process. So that is the integral minus the integral of dq reversible over t. Okay. And that, well, dq reversible is the negative of dw reversible, right? Because remember, dq doesn't matter whether it's reversible or not. Delta u is 0, dq is minus dw, and vice versa. So dq reversible is minus dw reversible. No, I'm looking at Karen. So do you understand delta u is 0 because the temperature change is 0. Delta t is 0.
Because no work's being done. Right?
No, there is
Oh,
work.
no, because the temperature, right?
Because the temperature is not changing, and this is, and for an ideal gas that's not undergoing a reaction or a phase change, and the temperature change is 0, there is no change in internal energy. Because remember, it's like 3/2 RT, right? So, okay. So dq and dw are always negatives of each other for this process, this type of expansion, isothermal expansion, whether it's reversible or not. If it's reversible, then the reversible heat that's transferred is a negative of the reversible work that's done. The amount of heat that goes in is the same as the amount of work that's done. We've learned that already. That's from the first part of the semester. So this negative dq rev is actually dw rev. And this is just a fancy way of writing, well, dw is minus P external dV. But if we're talking about the reversible process, P external is equal to P gas, which we just call P. Right, so this is, so this is minus P dV over T. See, but this is all the steps to get there. And I can't, that pressure is not constant. This is the reversible. So this is minus nRT over VT dV, right? So this is nRT over V. Put that in, and now I can cancel the T's. So that's minus NR integral dV over V from V1 to V2. So that's minus, so what did we we're calculating delta S surroundings, oops, for an isothermal reversible expansion, and we're getting it's minus NR log V2 over V1, which if we use Boyle's law, because temperature is constant, we can replace V2 over V1 with P1 over P2. We've done this before. So this is delta S SIR for the reversible expansion. So did you notice we basically just did the same derivation twice, with the only difference being the negative sign? Because look, up here, we had delta S as NR log P1 over P2. We did basically the same thing up here. We had dq rev, we replaced it with the negative, let's go up further. dq rev is negative dw rev, right? And that's so dw rev is minus P external dV, but for reversible, it's minus P dV. And so here we have dq rev, which is the negative of that. And so that's just PdV. And you go down here and you end up with this formula for the delta S. Well, the delta S surroundings for the reversible process is just the negative of that. So this is just the negative of delta S. That's because delta S is calculated with the reversible path. So this has got to be the negative of it, because we know that delta S plus delta S surroundings is going to be equal 0 for the reversible path, because that's the second law. So we got the same formula with a negative sign in front of it. So that's very logical. We were supposed to get the same formula with the negative sign in front of it. So these are negatives of each other. And we like that because of the second law. That's the second law. Okay, so that's kind of the less interesting calculation, really, because we get this negative of what we already calculated. But what is delta S for the constant pressure, which is an irreversible, which is a spontaneous path? Okay. So let's figure that out. Actually, before I do that, I have something else here in my notes that I might as well put in here. And that is that I want you to recall that when we talked about the work of an isothermal reversible expansion, the work turned out to be minus nRT log P1 over P2. And the heat is the negative of that, which is nRT log P1 over P2. So you'll notice that it's just a T here that makes the difference between, see the T here between the Q and the delta S. The delta S is nR log P1 over P2. The Q is nRT. See, it only differs by the temperature in this particular case. That's not true in general, but maybe you've noticed that these little derivations I've been doing looked a lot like stuff we've calculated before, because we've calculated the work, and the work and heat are negatives of each other. So they're very similar calculations, and the delta S and the Q are very much related because you've got that temperature in the denominator. But that's really the only difference, and that came right out of the integral. So that only made a difference with the temperature being here or not being here, right? Okay, so that's just delta S was nR log of P1 over P2, delta S sur minus nR log of P1 over P2. So this is all for the isothermal reversible expansion, all of these equations. All right, so now we're going to look at the constant pressure example. Okay, so let's say that we have, well, maybe I should calculate the delta S while I'm here. Sorry about that. Okay, so if I calculate, so suppose I have, I'm going to put some numbers in this problem. So suppose I have 1 mole of an ideal gas, and it's going to expand. Its initial pressure is 10 atmospheres. Its final pressure is 1 atmosphere. The temperature is let's say the temperature is 300 Kelvin, but actually T doesn't even come into the calculation of delta S and delta S, sir. It does come into the Q and W though. So delta S would be NR 8.314 joules per mole Kelvin times the log of P1 over P2. Okay, so that comes out to 19.1. And my units are joules per Kelvin. These units cancel out here, so I don't have to worry about that. And of course, delta S surroundings is just the opposite. It's just negative 1.00, 8.314 log of 10 over 1 comes out to negative 19.1 joules per Kelvin. And just to calculate the work and the heat while we're at it, the work is minus nRT log of P1 over P2. And it's negative 5.74 kilojoules. Just check. Yeah. And so really these two, these differ by the temperature here is the big difference in the calculation. And the Q is plus 5.74 kilojoules. All right. And the delta S total is equal to 19.1 minus 19.1 or 0, which works, right? That's what it's supposed to be for the reversible expansion. Okay. This course is pretty cumulative at this point because all of this stuff we did for the isothermal expansion when we weren't talking about entropy, we were just talking about work and heat. And now we have to throw in the entropy calculation. So now I'm ready to do the constant pressure expansion. So let's see. So delta S surroundings. All right, now, well, first of all, delta S is the same, right? Because it's for the reversible path, but delta S surroundings is for the particular path taken. So delta S surroundings is the integral of dq surroundings over T, which again, dq surroundings is the negative of dq for the system, which is that dq is a negative of the dw, because again, delta U or du is equal to 0 because the temperature is constant. This is an ideal gas, no reaction, no phase change. Notice this negative sign has disappeared. dq and dw are negatives. But now this is the constant pressure work, constant external pressure. So this is minus P external dV over T, right? That's dW, it's minus P external dV. Okay. And if you have, a system, it starts out at pressure P1. You have a constant atmospheric pressure here, P external, and it expands. So this is a smaller pressure inside and, sorry, bigger pressure inside. And it expands until the pressures are equal. Well, the final pressure is P2. And that it has to be equal to the external pressure. We've already talked about that. So P2 is really this external pressure here. And it's constant, so it could come out of the integral. And the temperature is also constant. So P2 is equal to P external. We talked about that already a long time ago. And temperature is constant as well. So they both come out of the integral here, and I'm left with just the integral of dV. And this is really just like what we did before for the work at constant pressure, except we didn't have the T in the denominator here. It was just minus P external dV. So this is minus P2 now over T times V2 minus V1. This is nRT over P2 minus nRT over P1. And this equation is going to look familiar, almost familiar to you. The T's cancel though. So I'm taking the NR, not the T is gone, the NR out and putting the P2 inside. So this is minus NR times 1 minus P2 over P1. And this is for the constant pressure isothermal expansion from P1 to P2. Okay. And now if I put in the numbers and calculate this, 1 mole, 8.314 joules per mole Kelvin, 1 minus, so P2 over P1 is 1 over 10. You can see that, that this is positive, 1 minus a tenth. This is 0.9. And this comes out to negative, because of this sign, 7.48 joules per Kelvin as the delta S surroundings for this constant pressure. So irreversible, spontaneous expansion. And remember, delta S surroundings, delta S system is the same as before, which was 19.1 joules per Kelvin. So now I have a delta S total that I can get by adding these two, and it comes out to a positive number, which it better come out to, because this was a spontaneous process. And so it has a positive delta S total. Shoo, that worked out. That's our first entropy calculation. So here are the summary of the equations for the isothermal constant pressure expansion. Okay, delta S surroundings. Same is minus NR 1 minus P2 over P1. Delta S system is the same as before. Okay. Just sort of for completeness, what was the equation for the work in a constant pressure expansion? Came out to minus nRT, 1 minus P2 over P1. This was derived earlier. And so the Q would be the negative of that, plus nRT. Okay. Yeah, we're about done. So for an isothermal expansion, I'm going to just put in a little chart here. Oh, I should calculate these numbers. So this work here comes out to 5.74 kilojoules negative, and this is plus 5.74 kilojoules. So you've done calculations like that before. And this is 300 Kelvin, and this is 1 and 10. Okay. So we're going to contrast the reversible and the constant pressure case. Okay, so we'll have Q, W, delta S surroundings, and delta S total. Okay. So we already knew before that there is a greater amount of work done in the reversible case, and this is kilojoules, than in the, oh, I put the wrong numbers down. I'm so sorry. I put the reversible numbers down, but that's not right. Just going to check it. Yeah, 2.25 kilojoules. And these are the same thing, but the opposite signs. The delta S is the same for both. But this is the one that's interesting, because while the delta S SIR is the same as delta S for the reversible case, it is not the same. Well, it's not the same, it's a negative of it. For the reversible case, it's not the case for the constant pressure. These two add up to give 0. But these two add up, oops, didn't mean that. These two add up to give a positive 11.6. Okay, so at least the second law is working for this simpler, this pretty straightforward example, although it's pretty daunting as a beginner, you know, I understand that. Yeah, there's a lot here. So your second law calculation is over. You could see that the delta S total was equal to 0 for the reversible, and that it was greater than 0 for the spontaneous or irreversible expansion, the constant pressure expansion. And so what we're going to do is work our way through other calculations like this, but not on this day. Okay, that'll be next time. I'll start working on that.
Dr. Cooley?
Yeah.
Does that mean that the entropy can never be negative at constant temperature?
Entropy can never be negative.
If it's 0, if it's reversible, Like the total entropy, sorry.
Oh, total entropy.
Yeah, sorry.
Right. So basically, yeah, it wouldn't be a spontaneous process.
Okay.
That's why when a reaction gets to equilibrium, it's like it just to continue forward would be to decrease the total entropy, and that doesn't happen.
And that doesn't make sense.
And you can approach equilibrium from either side, but once you get to that point, it kind of stops changing, and going forward, you would actually get a different, like in terms of delta G, delta G would start to increase, and then you would have to, it wouldn't do that. So spontaneously, delta S total has to increase. That's not to say that you can't have things happen that decrease total entropy, right? I mean, you run your refrigerator or whatever. I mean, you can use energy to do that, but we focus on spontaneous things. And so, yeah, you're right about that. Yeah, so, the next few classes, there is some, there's a lot of little details sometimes with this, like, when you're solving a problem and you say, okay, what's a delta S here? It's an irreversible case. You go, okay, what's a delta S? And then you have to remember it's the same as it is in the reversible case. So there's a bit of trickiness to it that takes a little while to get used to, but you get used to it. So I'm going to email a quiz probably tomorrow, probably not until late tomorrow. But I'll make sure you have time to do it. I'll give you a week and you could come back to me if you need more time. But Wednesday's a holiday next week. It's it's a day off. It's Veterans Day. So maybe that will be helpful to some of you to spend, be able to work on the quiz. Let me know how you're doing. If you need any help, you can always contact me. I can help you to a certain degree with a quiz. I can't give you the answers. So. But all right. I did post an assignment for this unit. But we have only done probably one of the things on that assignment so far. So we'll be working on it. I did look up to see if anyone else had submitted a critical micelle calculations, and I didn't see any more. And I didn't see any more urea labs submitted either, although I didn't check in the last day. So hopefully you'll be working on that and getting that in. That's going to be the challenge for the end of the semester, but it has to be done. Anything else? I'm done.
I have a question actually, that because the total entropy really won't be negative unless you have energy. Is that why? Does that come from the first law where you can't get energy from nowhere?
I don't think so. I don't think so. I don't think it has anything to do with the first law.
Huh.
Yeah. Yeah, I don't think so. It's really a different thing, this entropy thing.
Oh, I did have another question, Dr. Cooley. At one point during this semester, you had asked us to look up a literature value, and you gave us like the name of some kind of a database.
Oh, NIST?
Is that what it was?
Yeah.
Okay, because I've been having some trouble finding.
National Institute of Science and Technology, I think. It used to be called the National Bureau of Standards, but that's not what it's called anymore. But now if you type NIST and you type just the name of a molecule or chemical, you can get all kinds of stuff. Maybe it'd be better to type like standard enthalpy of formation, NIST. That's what I type, That's how I find my info a lot of the time. Yeah, usually it pretty much agrees with Wikipedia, though, I gotta say. But I always check there because, Wikipedia, not so good. So listen, if anyone needs help with lab or something, you're gonna have to contact me. All right, we got to make a push for that, Yeah. All right, I'm done. I'll see you next time.
Have a good night.
Yeah, you too. Bye.
Is there any special problems due today?
I think so. I think the feeder formation of aqueous ions, and there was one, I don't remember what I called it. It was let me check. I forget what it was called.
Oh, there was special problems due today.
They're due today. I always do take them late, but I want to be able to post the solutions.
Yeah, but
if you hand them in by Friday, I can post the solutions after that. That's
where are they?
I'm looking for it. Okay, when I find it, I'll share my screen with you. Yeah. I didn't put up the place to post them yet. But, hold on. Did I put them? Oh, here. Okay, I'll see if I can. Oh, that's the wrong thing to share. Here. All right, can you see that? So this is in the special problems folder. So if you go down here to special problems, then these last two, heats of formation of aqueous ions and the benzene acetylene reaction, I think.
Okay. Yeah.
Dr. Cooley.
Yeah.
I'm going to submit my lab report for the urea tomorrow, but I have a question for the discussion. Do you want me to include the discussion questions or just make it in paragraph format? Like, should I include the question with the answer?
Paragraph form. That's what you should do. Yeah. No, you don't have to include the questions. That would be silly. Just answer them, in paragraph form.
Okay, thank you.
You're welcome.
Have a good night.
You too. I'll share this one now. So this is the, wait. This is a benzene acetylene problem.
Oh, we know how to do this.
Oh, yeah, maybe if I look at my notes.
This is like what we were doing in class last week when we were working with product and reactants, right? This is the second thing.
Yeah, we were doing in class last week. Hold on.
Yeah, I remember those.
Let me, when did I assign it? I don't even remember. Was it?
I think it was October 26th. Well, I mean, that's when we started working on the, on that. Maybe it was later. Oh no, it was not. It was not.
talked about it.
Yeah, it was definitely last Wednesday.
Oh, see,
Yeah.
Wednesday next week, I said. So that's the benzene acetylene problem.
Mhm.
And then there was the one I think we got to at the very end. Ugh.
Heating up ion molecules.
Yeah, aqueous ions. Where did I talk about the special problem? Oh, I know I did. Oh, here. There. Yeah. But those are both posted under special problems. Okay.
Yeah, I found them after.
And I have to go and put up right now. I'm going to put up the place to submit them.
Oh, good. Yeah, I have the notes for that, so I should. Yeah, that'll be easy. Those weren't that hard.
No, they're not that hard.
All right. Thank you, Dr. Cooley. Have a good one.
All right. Bye-bye.